So this is hopefully a short little video introducing the quotient rule. So you can see it sitting in front of you. This is a rule that applies to any time you have a function that's made up of an expression divided by expression, and both expressions have a variable in them. And I'm going to start off by showing you some examples, but the first example I'm going to show you is you don't have to use the quotient rule. So like, for example, let's say we have 1 over x squared. Now, when you first look at that, that's a fraction. You got an expression divided by expression, but notice the top expression does not have a variable in it. So the way I would not use the quotient rule on this, the first thing I would do is I would rewrite it as x to the negative 2, because that's just another way to write it algebraically. And then, of course, I'd just use the power rule to find that. However, you could use the quotient rule here. But the example that's more likely where you'd use the quotient rule would be something like sine x over cosine x. Right, there's a... Now, once again, actually, you could turn this into, if you remember your trig ideas, you could change this into tan x, and if you know the derivative of tan x, then you don't need the quotient rule. However, at the same time, if I've forgotten the derivative for tangent x, I can always turn it back into sine x over cosine x and just use the quotient rule. So some other examples would be where you could use a quotient rule but don't have to. So for example, this is a good one, 2x squared plus 3x minus 5 divided by x squared. You absolutely could use the quotient rule here, but you could also just turn this into 2 by dividing x squared into each one, plus 3x to the negative 1 minus 5x to the negative 2, and use the power rule to derive that. So whether you use the quotient rule here or make this little algebra move first and then use the power rule, you should get the same result. Okay? But let's focus on ones where we actually have to use the quotient rule. Like, for example, let's say I have e to the x over cosine x, for example. Okay? That's a case where I'm probably going to need, there's no way to simplify that. Well, okay, that's not true either, but we'll talk about that in a minute. But this would be a good candidate for the quotient rule. So now the quotient rule is a little bit more complicated than the product rule. The product rule, all you have to do is remember to take the derivative of 1 times the other plus the derivative of the other times 1. So that's pretty easy to remember. The quotient rule is a little bit more complicated because you got something similar to the product rule, but then you're dividing by something squared. So this is a little bit more complicated. At this point, I can't remember whether I made this up or I heard it from someone and stole it, but I made up a little rhyme that goes like this. Low d high minus high d low all over low squared. And so, of course, in this case, the low is the bottom of the fraction and the high is the top of the fraction. So see if you can follow along. This is low d high, meaning the derivative of the high, minus high d low, meaning the derivative of the low, all over low squared. Okay? And you can even turn it into a little rhyme like low d high minus high d low all over u squared or something like all over low squared or something like that. But anyway, of course, you don't have to use this little rhyme or whatever. But if it helps, why not? If you have if you had another calculus teacher that was maybe more creative than me and had a better system, that's great. Maybe you could share that on the discussion that's going on right now. But whatever it takes, you got to get this down. Now, where a lot of people make a mistake is they get these two switched. That's a problem, right? Because in this case, in the product rule, it doesn't matter if you get the two things switched because addition is not commutative, which means you can add in any order. Subtraction, however, it does matter if I'm subtracting one from the other because I'll get a negative result or an opposite result. So you got to remember, in the first one, I'm taking the derivative of the top, and in the second one, I'm taking the derivative of the bottom. Okay, so let's apply this to this one, this h of x. So if I'm taking the derivative of this, and I'll just use this notation this time because I haven't used this notation yet. So in this case, we would say that this is like my f of x, right? And that's like my g of x. So I could go to the side here and say f prime of x would have to be e to the x, dx dx, which is just 1. And g prime of x would be negative sine x. So now I know what my g prime and f prime are. So now I'm just going to write them out because I know that this has got to be g of x times f prime of x minus f of x. See how small that prime was? It's easy to lose track of. G prime of x all over g of x squared. So now I'm just going to start plugging in the things that I want. So h prime of x would be equal to g, which is cosine x, times f prime, which would be e to the x, minus f, which is e to the x, times g prime, which would be negative sine x, all over g squared. Remember, g is cosine, so that would be cosine squared. So there's the product or the quotient rule. Clean this up a little bit. I don't like the e to the x on that side. I like it on the other side. Not a big deal. This is e to the x, cosine x. But here you do need to clean this up because we have a negative and negative and there's being multiplied. So you don't want to leave this like that. I would change that to a plus e to the x sine x all over cosine squared x. And that would be my simplified form. Okay? Let's do another example. Let's say we have y is equal to 5 to the x. Let's bring some of those more obscure ones in here. Over, let's say, x squared plus 2x. Okay? So here's an example of good candidate for the quotient rule because we have expression on top of the fraction that involves an x, expression on the bottom of the fraction involves an x, so I can use the quotient rule here. So I'm looking for, so first of all, I want low, which would be x squared plus 2x, d high, which would be the derivative of 5 to the x. So remember that's the natural log of 5 times 5 to the x. And I'm subtracting that. So this was low. This is d high, right? Minus high, which would just be 5 to the x. And then d low, that would be 2x plus 2. And on the bottom, we have low squared, which would be x squared plus 2x squared. Okay? Now I need to clean this up a little bit. Whoops, that was not y, sorry. That should have been dy dx, right? So, still writing dy dx. Let's clean it up a little bit. So we got natural log of 5 times 5 to the x times x squared plus natural log of 5 times 5 to the x. Whoops. Multiply that 2. So that 2 would be multiplied by, that 2, I'm sorry, would be multiplied by the natural log of 5. So that would be 2 ln 5 times x times 5 to the x minus, and then down here I'm going to have 2x times 5 to the x plus 2 times 5 to the x all over x squared plus 2x squared. Now normally this is not considered simplest form, this bottom, you normally multiply it out, but in my class we're going to make a rule you don't have to multiply out a binomial raised to a power. So and I mean it'd be easy to multiply this one out, but I just make it just so it's a simple rule. In simplifying, you don't have to raise any binomial out to power. Now sometimes you might want to because it'll just make the simplifying easier, but in this case you could leave it like that. Now, one other thing we could simplify further, if you remember your log rules, And some of you probably won't be excited about this, but you can get excited. This here, 2 ln 5, remember I can take that 2 from out front and write it as a power. So this is really ln 5 squared, which of course is actually natural log of 25. So I could rewrite that as the natural log of 25 times x times 5 to the x minus 2x times 5 to the x plus 2 times 5 to the x. Of course, that whole thing is over x squared plus 2x squared. Right? So there's an example of, a couple examples of quotient rule. Now, I promised I'd talk about this a little bit. Sometimes people really don't like the quotient rule. And let's say we have something like this, x over e to the x. Now this is a case where I probably would avoid the quotient rule because it's fairly easy to rewrite this using algebra as x times e to the negative x. Hopefully you can see that those two are both, they're algebraically equivalent. And once I do this, then this becomes the product rule. So dy dx would be equal to, so this would be the derivative first, 1 times e to the negative x plus x times the derivative of that, which would be negative e to the negative x, which of course will simplify to e to the negative x minus x e to the negative x. Okay, let's take a quick look at how the quotient rule will produce the same thing. So I'm going to do this using the quotient rule. dy dx is equal to, okay? So quotient rule would say low, which is e to the x, d high, which would be times 1, minus high, which would be x, times d low, which would just be e to the x, all over low squared, which would be e to the 2x. Okay? So now, when we go to how do we get these to be the same? Well, let's look at what this is. This is actually 1 over e to the x minus x over e to the x. That's another way to write that, right? So we could combine this to one fraction as 1 minus x over e to the x. Do you all buy that? Still doesn't look like this one, but notice down here I can factor out an e to the x, so that'd be e to the x times 1 minus x all over e to the 2x. And of course, this one of these e to the x's will cancel with one of those, and this would be ended up being 1 minus x over e to the x. And you can see now they are the same. Okay? Both involve a little bit of algebra, both before and after taking the derivative, but they do produce the same results. All right.